All right, we're going to start the logarithmic function here. Definition of the logarithmic function: with a base a, f of x equals log, and then you put a little subscript here, a, that's the base of it, of x, is the inverse, all right, the inverse function, inverse operation of the base a. Notice, again, still base a, we're using that same thing, of the base a exponential function y equals a to the x. And so what we mean by this is, say something like something similar you're probably used to is, if we had the function 7x equals y, how do we undo this 7x part, right? And the way we do that and just get the x is the inverse operation of multiplying by 7 is dividing by 7. And so we would apply a divide by 7, which is multiplying by 1/7, to everything, and you'd end up with 1/7 times 7x equals 1/7 times y, and you just get x equals y over 7. And so that got us just the x, because the 1/7 is the inverse of the times 7. And so similarly here, if we have something like a to the x equals y, we can get that x by itself by applying a log of base a. So our exponential a to the x has a base a, and our logarithm then has to have a base a down there. So these two right here, this has to match this, and then they are inverses of each other. And what it does is that log basically undoes that exponential, and we just get the x on that side, and then on the left, it's log base a of y. Okay? And so that's essentially how this works. It just undoes what we already have there and gives us just the x. It undoes exponential function. You can see in this graph here, this is the line y equals x, and as we talked about before, inverse functions mirror image across that line. You can see here in blue, we've got the y equals 2x function. That's the exponential function. And then look here in yellow, we've got y equals the log of base 2 of x. And you can see it is just mirror imaged right along this red line here, this red dotted line, y equals x. They are mirror image straight across it, like you could fold it on that dotted line, and the blue and yellow lines would just fold right on top of each other. Okay, so that shows right there, their graphs show that they are inverses of each other. So two special logarithms and some algebraic properties here. First, log base 10 is typically just written as log of x, where we don't bother writing it in. This is called the common logarithm, and because it's so common, people got tired of always writing a base 10. It's common because we have a base 10 number system. We have, we count by 10. We have 10 fingers, and so the log base 10 is a very common one to use right there. Most of your calculators, if it just has log written there, it is going to be this log of base 10. There are some textbooks and sources you might find, like on Wolfram Alpha or stuff like that, where you have people that are, from different countries. They have different things where this log written log like that is actually the natural logarithm, which is the one I'm about to talk about. But mostly here in our country, log is just log base 10. The next one, log base e, where e is that natural exponential, the Euler's number, and it is actually extremely useful. And log base e is typically written as ln of x, or sometimes you just write ln of x like that. So this one up here is log of x. This one's called ln of x, or ln of x. Those are parentheses I'm putting around it. And it's operating on that x. And it's called the natural logarithmic function. It's actually extremely useful and shows up in a lot of areas. So note that natural log of x equals y implies then that e to the y equals x. This comes from the idea that e to the natural log of x is going to equal e to the y. So just like how that would be like the in-between step to go from there to there. Just like how we could take the log of an exponential to get rid of the exponential and just get our unit out of it, like log, oh, well, let me do this one. Let me do natural log of e to the x is going to be x. We can even do e to the natural log. We can use exponentials to undo logarithms, like this. All right, and we can take logs and put them up in exponents, and that'll undo the log and give us just what we have there. In particular, if we set x equal to e, we obtain the natural log of e equals 1. If you want to try that, you can think of this way as e to the natural log of e equals e to the 1, and that's just e equals e. So you can see there it undoes it just like before. All right, because e to the 1 equals e. There you go. And so what we've got here is some algebraic properties of these. For any numbers b greater than 0 and x greater than 0, the natural logarithm satisfies the following rules. These rules also are going to work for regular old logarithms as well. It doesn't just have to be natural logarithms. And so the natural log of b times x equals natural log of b plus natural log of x. Be very careful that you don't take natural log of b times natural log of x. So in other words, don't do this. Don't think natural log of b times natural log of x equals natural log of b times x. Like, it doesn't work that way. That's wrong. Don't do that. It's natural log of b plus natural log of x equals natural log of b times x. And again, like I said, this works for other log bases, like log base a of b times c could equal log base a of b plus log base a of c. So it works for other bases as well. All these rules doesn't have to just be natural logarithm. Natural log of b divided by x is natural log of b minus natural log of x. Similarly, natural log of 1 over x equals negative natural log of x, and this is simply putting it into rule 2, because rule 2 would say that this is natural log of 1 minus natural log of x, and natural log of 1 is just 0. So this is just going to be 0, right? That's 0, and so it's just negative natural log of x. So 3 is really just a special case of 2. And then here, what we have is kind of a special case of 1, because it's natural log of x to the r. And I'm going to write this down here. So it's natural log of x to the r, which is just going to be natural log of x plus natural log of x plus natural log of x, r number of times, right? However many times there are r number of those natural log of x's plugged together, which is just going to equal, well, if say r was 5, we'd have natural log of x plus 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 a natural log of x. That's 5 natural log of x's. It'd be 5 natural log of x. So in this case, it's just going to be r times natural log of x, because we'll get r number of these natural log of x's added up together. So that rule is really also just a case of rule number 1. So really the one you need to worry the most about is rule number 1. And then if you get really good at them, you can, rule number 1 and rule number 2, if you get really good at these, you don't even really need rule number 2. You can always go back to rule number 1 if you really get good at these logarithm things. All right, use the properties of logarithms to simplify the following expression. So we're going to use these properties from before. So we have natural log of 4 minus natural log of sine of x. And actually, I think this should have one more thing on it. I'm not sure why it's there. We're going to add on natural log of cosecant of x. Okay? And so if we look at this, these are being subtracted, so we can do natural log of 4 divided by sine of x, excuse me, times cosecant of x, like that. And sine times cosecant. Remember, cosecant is 1 over sine. So sine of x times cosecant of x is sine of x times 1 over sine of x. So that's just going to be a 1, which means this will just be natural log of 4. Okay? So that would be that answer right there. Next one, natural log of 3x squared minus 9x plus natural log of 1 over 3x. So we're doing a plus. This means that we can put them in one logarithm multiplied together. So this would be 3x squared minus 9x times 1 over 3x, just like that. And then we can do natural log of 3x squared minus 9x over 3x. We can cancel out one of the x's. We can divide by 3, and we'll get natural log of x minus 3. Okay, and that one will work out like that for you, so not too bad. These ones, I'll do one of them and I'll leave the second one for you because this is expanding them out. So in a similar fashion, we want to use the rules but use them backwards. So we have two things being divided by in a natural log, which means I can just split them and make it minus natural log of 2x minus 3. There you go. And so I'm going to let you try natural log of 1 over 8. Try doing that, and then I'll put the answer in the actual notes when I do it. And I'm going to add one more. Do a C. Let's do this one. Try something like natural log of ax squared over t plus 2. And again, I'll put that one in the notes. Then I do it, or maybe I'll just go ahead, yeah. I'll just put that in the notes and I'll go ahead and do this natural log of 1 over 8. So this is going to be natural log of 1 minus natural log of 8. We can replace the division with a subtraction of two natural logs like that. Natural log of 1, that's just 0. And so we just end up with negative natural log of 8 right there. Okay? So that would be the answer for that one. That's going to be our answer for that one. And then try this next one I put there for you and see how that goes. Next is some inverse properties. These I was already talking about, where these logarithms undo exponentials and exponentials undo logarithms. That's these right here. You have to make sure the bases stay the same. So really we only need rule 1. Rule 2 is just a special case where we're making the base A, B, E. So anyway, what we can do is a to the log base a of x is just x. I showed that a few pages back. It just undoes the logarithm. It pulls the x out of it by putting the log in the exponent of the same base. And then reverse like the log of base a of a to the x. As long as those a's match, will be x. So be careful. You need to make sure this a, this a matches that a, and then they undo each other. And then the same thing here. This A has to match that A, and then they undo each other, okay? And then, again, rule 2 is just doing the same thing, but with base E's as well. So simplify the following expressions. I'll do the first one. I'll leave the second one for you. E to the natural log of x minus natural log of y. Well, natural log of x minus natural log of y is natural log of x divided by y. And e to the natural log of x, that's this right here, is just x. And in this case, it's our xy. So the e is going to undo the natural log and just give us what's on the inside of the natural log, which is x over y. All right, try the next one, and I'll have it completed for you again in the notes to look at. Solving exponential and logarithmic equations. So I'll do one of these and leave the second one for you to try. So the first one is solve for y. Natural log of y minus b equals 3t. So I have a natural log. I want to get rid of the natural log. I want to undo that natural log and get the y out of it. So I'm going to raise both sides. I'm going to put them in the exponent of the inverse of natural log, which is just e, the base of the natural log, which is e. And I get e to the 3t like that. So I put both sides raised up to the exponent e there, or not raised the exponent, in the exponent of e. And then here, these are going to just undo each other on the left-hand side, and you'll get y minus b equals e to the 3t. And then you get y equals, just add b to both sides, e to the 3t plus b. And that's it. We've solved it for y. So again, you try number or letter B there. It says solve for K. So try and solve that for what K equals. And again, I'll have the answer in the notes written out for you. Next, changing bases. This is a great thing because the calculators you use should probably only be able to do base 10, maybe base E as well, natural logarithms and regular logarithms. But you're not going to go through and do, like if it's log base 7 or log base, 3 or something like that. So we need to be able to do something with those. And this is the change of base formula. And so what this basically does for us is, and I'm going to write it up here a little more fully, this one just tells you how to change it to natural logs. Log of base A of x can equal log, and then you can pick whatever base you want. So we'll put like a C here and do the log base C of x, so we placed A with C, and then divide that by log base C again, but this time of A. And take note of what matches here. This is this base. This is the color over here. This is this, and then the C, these two have to match. And it can be whatever you want. It can be any base that you want it to be, and it'll always be true. And in this specific change of base formula given here, obviously they chose log base E as C. They did log base E like that. And again, the top and bottom log have to have the same base, any base you want, which is just natural log of x over natural log of A. And that's what they did there in that example. So let's try this one. Express the ratios as ratios of natural logarithms. So we have log base 9 over log base 3 of x. And so the way we can do this pretty easy is we want to change everything's base to natural logarithms. So log base 9 of x is just going to be natural log of x over natural log of 9. Okay, and then we're going to divide that by log base 3 of x. That's going to be natural log of x over natural log of 3. Okay, and then it's just a matter of we're dividing by a fraction, so that's the same thing as multiplying by its reciprocal. So natural log of x over natural log of 9 times the reciprocal of what's on the bottom, which is natural log of 3 over natural log of x. And the natural log of x's right here, they will cancel. Okay, they cancel, and we're left with natural log of 3 over natural log of 9. And if we wanted to take this a little further, we can say, well, 3 is just, or 9 is just 3 squared. Okay, and remember a few pages back, what did we have here? Where was that? We had this rule right here, our power rule, where if we had what we were taking the log of had an exponent, we could actually bring that exponent out in front. Okay, so over here, where was I? Where we were here, this actually becomes natural log of 3 over 2 times the natural log of 3. And so the natural log of 3's can cancel, and we're left with just 1/2. So that whole thing all reduced just using our log rules down to 1/2, which means that log base 9 of x over log base 3 of x is just a constant. Y equals, so if we were to actually graph this, log base 9 of x, and you can try this if you want to try it on a graphing calculator or Wolfram Alpha or something like that. You can try graphing this, and you'll find this just equals 1/2, which means if you were to graph that function, right, if this was the 1 value right here, right, here's our x line, here's our y line axis, this is just going to be, this graph here is just going to be this horizontal line right there through 1/2. Okay, that's that function. That's this right there. Okay, do that in blue. That's that function right there. Turns out to just be a constant. Okay, here's a problem for you. Find a formula for the inverse function where, I don't know why that $sign is there, but where f of x equals that. Maybe I could block that out with white instead, so I don't know why that $sign turned out to be there. Where f of x equals 100 over 11 plus 4 to the negative x. So remember, when we're finding inverse formulas, we want to swap the x's and y's. We're going to make this, we're going to say this is y, so y equals 100 over 11 plus 4 to the negative x. And we're going to swap x and y. So this will be x equals 100 over 11 plus 4 to the negative y now. And so now we just need to solve for y. So this was the swap x and y, and now we're going to solve for y. And so the first thing we want to do is get that y out of the denominator. So I'm going to multiply both sides by 11 plus 4 to the negative y, and divide both sides by x. And when I do that, you get 11 plus 4 to the negative y equals 100 over x. All right, you should be able to do that one. Now, I'm going to subtract 11 from both sides to get the 4 to the negative y by itself. So 4 to the negative y equals 100 over x minus 11, just like that. And now I have that y up in an exponent, and I need to undo that exponent. So I'm going to undo that exponent using a log with the same base. So log base 4 of 4 to the negative y is just negative y. And then over on this side, it's log base 4 of 100 over x minus 11. That's it. Just apply that logarithm of base 4 to both sides. And now we have that negative 1, so I'm going to have to multiply both sides by negative 1. And so then this will be negative 1 times log base 4. Now I won't always write that negative 1 out in front like that. I'll probably just usually put a negative sign, just like that. I can go ahead and actually combine inside the logarithm right here. I'm going to make these have the same base, so I'll multiply top and bottom by x for that one. And I'll end up with negative 1. I'm writing it that way for a reason. Again, in the future I won't do that. Log base 4 of 100 minus 11x over x, just like that. And now I have that negative 1, and what I can do is use that same power rule in reverse, and I can take this and I can actually put it up here as the exponent of what I'm taking the logarithm of. So this becomes log base 4 of 100 minus 11x over x to the negative 1. Just like that. And yeah, just like that. And so anything to the negative 1 power is just that reciprocal of it, which means ultimately we get y equals log base 4 of x over 100 minus 11x, right there. And then the last step is simply to replace the y with f inverse of x equals log base 4 of x over 100 minus 11x. And there you go. There's our inverse function. That inverse function would undo the other function. Okay? All right, so the half-life of a radioactive element is the time required for half of the radioactive nuclei present in a sample to decay. It is a notable fact that the half-life of is a constant that does not depend on the number of radioactive nuclei initially present in the sample, but only on the radioactive substance. And the answer is, well, if you want to think about this, think of if you had, say, 100 coins and you were going to flip them. And so you took your 100 coins and you flipped them all. And every time one landed as a tails, you threw it away. So if you flip 100 coins, the first time you should end up throwing about 50 of them away. You're going to end up throwing half of them away that turn out to be tails. And then if you take that 50 again and you flip them again and again throw out all that turn out to be tails. Now you're flipping 50 coins, you flip them all. Well, how many do you expect to throw out in the second one? Well, not 50 again, right? You expect to throw out about 25 of them because about half of those 50 will turn out to be tails and you throw them out. Then you've got about 25 left. And so you flip them again and throw away all the tails. Are you going to throw away 25 of them? No. You expect to throw away 12 or 13 of them, somewhere in the middle there. And so this is what radioactive decay is like. Every time you do a half-life of it, you have a chance that, any individual one has a 50 chance of decaying and being basically thrown away, just like the coin flips. So, why? Let y naught be the number of radioactive nuclei initially present in the sample, then the number y present at any later time, t, will be, so we're going to start with A equals A naught, that's our initial amount, times e to the negative k times t. Okay, this is going to be our function for it. And this graph is an exponential graph, and it's going to look like this, where this is the a-axis and this is the time axis, a being the activity or the amount. And we start with an a naught amount. That's when t equals 0. When t equals 0, this is e to the 0, which is just 1, and a equals a naught. So that's going to be our initial amount right there. And then as we move, this is going to decay. This is an exponent, a negative exponent. And as you remember, regular exponents, they looked like this. And with a negative exponent, they looked like this, a mirror image across that y-axis, right? So this is like a to the negative x, whereas this was a to the x. So we have this one down here. This is our current situation. And so get that out of the way. So we have only looking from time t equals 0 on, it's just going to be this little decay part right here, where it decays down closer and closer to 0. And what we're interested in is when a equals 1/2 of the original amount. That's going to be our half-life. So we'd come down halfway. This is a naught over 2. This is our half of it. And we'd come across to here. And then whatever time this would be t with a little subscript 1/2. This is the half-life right there. That's the amount of time it took for half of it to go away. If we were to step forward that same amount of time again here, say we step forward, this was our time. If we stepped forward that same amount of time again, what we'd end up with is half of our other half. So this is half of that kind of a thing. So we can keep stepping forward half-lives, and it should just keep keep cutting it in half. I'm gonna get rid of all that red on there. And so we can go through and try and solve this out. So we want a naught e to the negative kt, where k is just some constant we've talked about, and we want that to be equal to the amount left is half of the original amount, okay? I kind of flip-flopped these, sorry. This side's over there and that side's over there, sorry. But anyway, we can get this out of the exponent. First thing we can do is cancel out these a naughts. They're gone. It doesn't matter. So in other words, what this math is telling us is the initial amount that you have does not matter for the half-life. Just like if I started with 100 coins, I'd get rid of 50 after one turn. If I started with 1,000 coins, I'd end up getting rid of about 500 after one turn of flipping. So the initial amount is not going to matter, or even the current amount isn't going to matter for how much decay or for how long it takes for half of them to go away. So those will cancel. If I want to get rid of this, I have an e, right? So I'm going to take and do the natural log of both sides. Natural log of e to the negative kt is going to equal the natural log of 1/2. And natural log of e to the negative kt is just negative kt. Now, remember that natural log of 1/2, I can write this as natural log of 1 minus natural log of 2, which is just natural log of 1. That's just 0. And so this is just negative natural log of 2. And so I have negative kt equals negative natural log of 2, which means t equals, right? We can cancel out the negative signs, which means t just equals natural log of 2 divided by whatever k constant that is. And that constant is going to help determine what that half-life is. And there you go. That would be our basic half-life formula, where this t, I guess I should have put in here, this is t 1/2. It's half-life t. That's the time for half of it to decay like that. There you go. T sub 1/2. All right, so the next one tells us the half-life of a certain radioactive substance is 48 hours. There are 20 grams present initially. Express the amount of substance remaining as a function of time. When will there be 11 grams left? So I'm going to leave this one for you to try using what we just did on the previous page, right? We've got our half-life formula over here. Try using this information to solve it, and I will write out the solution for this for you to look at in the notes. All right, and then you can ask me any questions you have on it later. All right, inverse trigonometric functions. The 6 basic trigonometric functions. You know what I'm going to do this? I'm going to do this in a separate video. So we're going to go ahead and stop this one here, and that'll be that.